Yeah, so now it's time actually, so we can start. And it's my pleasure to be chair for the next half of this day. And it's my pleasure to introduce Peter Dragnev from Purdue University, Fort Wayne, who's going to speak about the Mastodon Theorem.
Yes, Mastodon is actually the mascot of my university. They found some old Mastodon bones, maybe about a half a century ago, and that's when they decided that this is going to be the mascot. And later in the talk, you will figure out why that theorem, what is the Mastodon Theorem and why it's called Mastodon Theorem. And pretty much we are going to prove that Mastodon Theorem in n dimensions. And this is a joint work with Oleg Musin. And I want to thank the organizers for giving me that opportunity to speak today. So let's get started. The Thomson problem dates back to the beginning of the previous century, and it's Thomson's vision of the atom as a fixed model. It's sometimes referred to as plum pudding model of the atom. And if you assume that the electrons interact inversely proportionally to the square of their distance, eventually you end up with minimizing the risk energy, which is the summation of all possible distances, the reciprocals of these distances, and the weight is a power of S. That's why it's called S energy. And the Thomson problem is when S is actually 1 in 3D. As S approaches infinity, one can consider, as S approaches infinity, this is going to be the best packing of, endpoints on the unit sphere, or in this case on S2 in R3, which is a well-studied problem in discrete geometry. And when S approaches 0, the other near case, the other limiting case, then we have to differentiate that potential, and we end up with a logarithm, which really is equivalent, minimizing the logarithmic energy is equivalent to maximizing the product of all possible distances, also a well-known problem. It's referred also as White's problem from a paper of L.L. White from 1952 in American Monthly. And the White's problem, the results are known for n from 2 to 6 and 12. These are rigorously known optimal logarithmic energy codes. The Thomson problem, which is when S is 1, is also known for these values. The Fesch-Toth problem, when S is -1, which is to maximize the sum of all possible distances, and I should say that the distances are Euclidean distances. This is known for the same values. And the Thomas problem, when S approaches infinity, that's the best packing problem. The solution is known from 1 through 12. 13 and 14 was recent contribution of Oleg Musin and Tarasov. And 24 is actually a nice paper by Robinson from 1961 that establishes the maximizing the minimal distance for 24 points on the sphere. And as S approaches this as S approaches infinity, the solution of the Thomas problem is also what we refer to as maximal code, spherical code. Now, universally optimal codes is work by Kumar and Khan and Kumar from 2007, and it shows that if codes, spherical codes, are also sharp codes, then they minimize all of these different potentials and more, all of the so-called absolutely monotone potentials of the inner product between the points. And the first non-sharp situation is n equals 5. And there are still plenty of open problems in that first case. So the competing configurations are the bipyramid, which is north-south and equilateral triangle on the equator, and the square pyramid, which is north pole and a square at different height, different latitude. So when S is 0, I proved, along with two of my colleagues from the university, that the bipyramid is optimal configuration. It minimizes the logarithmic energy. And later on, when the 5-point problem was more people started studying the 5-point problem, Ed Saf referred to this as the Mastodon Theorem. That's where the name comes from. For those of you that may not know Ed Saf, they just recently published a book with Hardin and Borodachov on discrete energy. And I expect this to become a standard reference in the future for any minimum energy problems of this type. So when S is -1, then a computer-aided proof by Hao and Shao derived that the bipyramid is the best solution. And when S is 1 and 2, also a computer-aided proof by Schwartz from 2013 established the result. There are some limiting considerations by Bondarenko, Hardin, and Saf. And recently, Schwartz continued investigating this problem in a monograph of about 200 pages. He derived indeed the optimality. But again, this is a computer-aided proof, and very little can be done without aid of the computer. And the only solution without the use of the computer is still the 2002 result, and this one with Oleg now in the n-dimensional case. So this is the Melnick conjecture that there is this critical value of 15.04, Melnick et al. From 1977, for any value of S that is smaller. The Melnick conjecture now is proven by Richard Schwartz. The bipyramid is the best optimal configuration, and for S greater than 15.4, this is still open problem. Actually, a little bit larger than that value. Now, the Mastodon theorem in S3 and S4, that stems from a result of mine from 2016, and I'll briefly say a few words about it. So think of these points are on the unit sphere, and xi and xj are called mirror related in a configuration of points if the distance to all the others is the same. It's as if the hyperplane, the bisector hyperplane, contains all the other points. okay? And the characterization of D plus 3 log stationary configurations is the following. A log stationary configuration is either degenerate, so think the pentagon on the equator, that would be a degenerate configuration. There exists a vertex with all edges stemming out being equal. This is the 1-4 pyramid or the square pyramid. And every vertex is mirror related to another vertex. Actually, from C, one easily derives the Mastodon theorem, because that's the only possibility is when you end up with two simplexes, one will be a segment and the other will be equilateral triangle, but are orthogonal, all right? So mirror relation is equivalence relation, and the equivalence class forms regular simplex in the spanning affine hyperspace. That's a remark. And then with this, we end up with the result for S3, that's 2-3 configuration, which is one simplex of two elements, 2 points, and one simplex, regular simplex of 3 points, orthogonal to each other. That's really the north-south pole and the regular triangle, the equilateral triangle. In the S3, that's actually two orthogonal equilateral triangles. And in S4, one ends up with a triangle and and tetrahedron, both orthogonal to each other, as the result. Okay? Any questions so far? Hearing none, I continue. Yes?
Yeah. Do we have a question?
No. I just said that everything is clear.
Okay, perfect. We move on. Now, the result with Oleg, up to orthogonal transformation, every relative minimum, and I'm talking about the relative minimum, of the logarithmic energy of D plus 2 points on SD minus 1 consists of two regular simplexes of cardinality M and N, without loss of generality. Obviously, M could be assumed to be larger than N. Then the sum M plus N will be D plus 2, such that these simplexes are orthogonal to each other. The global minimum occurs when M is N, if D is even, and M is N plus 1 otherwise. So really, whatever we had here in 2016, that same goes in D dimension on SD minus 1. The only two other classes of minimal energy configurations that are known, that we have, for any number of points and any dimension, these are the regular simplex D plus 1 points on SD minus 1 and the regular cross polytope 2D points on SD minus 1. But they both are universally optimal, and their universality implies the minimization for the logarithmic energy. So in some sense, this is the third class of points, number of points in any dimension on the sphere that minimize the logarithmic energy. Now, a point configuration is called degenerate if it is contained in affine hyperplane. And again, think the pentagon in S2. So if N, we are considering first the non-degenerate, non-equidistant case. So if you go back to that 2016 classification, we don't want a configuration to be degenerate, and we don't want to have a point that is equidistant to all the others. So let n be d plus 2 be a non-degenerate stationary logarithmic configuration. Suppose there is no point x from that set that is equidistant to all the others, then x can be split into two sets such that these sets are vertices of two regular orthogonal simplexes with the centers of mass in the center of SD minus 1. So this really strengthens the characterization very significantly, okay? Before we knew that we have only mirror relation, but that would not discard the case of 3 or 4 or 5 simplexes that are orthogonal to each other. So this reduces it to 2, and this is the key. So in general, if we have some potential interaction function, the H energy is given as the sum of H of the inner product of distinct elements, okay? And the degenerate case is never a local minimizer for an energy of H energy. So let X be a degenerate configuration of a strictly convex potential function. Then there exists a continuous perturbation that decreases the H energy, EHX. Now, think the pentagon, all right? So then take one side, regular pentagon on the equator. Take one side and just flip it vertically, okay? And that will decrease the logarithmic energy or increase the product of the distances. All right, so this is really what this theorem is about. Now, the equidistant case is the following: a non-degenerate stationary lock energy configuration of type, since we can reduce it to a lower dimension. If one point is equidistant to all the others, then we can take the hyperplane that contains all these other points, and its intersection with the sphere is a hypersphere of different radius. So this problem really can be reduced to the case where we have really one equidistant point to all the others, and then the other points form a KL split in simplexes. So such non-degenerate stationary log energy configuration is a saddle point. And the way that one can perturb things, let me finish with the statement. Moreover, there is a continuous perturbation that decreases the logarithmic energy of the one KL part to the of the configuration to either K plus 1L or KL minus L plus 1 simplex. So let me explain in the 3D situation. So if you start with the square pyramid, if it's a lock energy, critical configuration, the partial derivatives are 0, then that height will have to be at -1/4 latitude. Okay? So what you do is you find one of the simplexes, which is one of the segments, move it up, and then move the other segment down a bit until that segment reaches the one that we're moving up, reaches the equator. Okay? And that will become a 3-2 optimal configuration. And you can do this continuously by decreasing the energy. Okay? Eventually, by perturbing from such a stationary configuration, by perturbing things, one can get to the two simplexes, which is the next step. So what are the techniques? The techniques is that for logarithm, there is magic that happens. That is why we can prove things without computer aided, without computer help. So when you differentiate, if we denote Rij to be 1 minus xi xj, which is really the distance squared between xi and xj, divided by 2, then differentiating with the Lagrange multipliers, one gets these vector conditions. Now let me explain these vector conditions. These are the forces that xj exhibits on xi. Xi can be considered fixed, and the sum of these forces will have to point outward on the sphere, otherwise xi will move. So there is that constant lambda I that this sum should be equal. Of course, this follows from differentiation as well. But when you sum these, what happens is you get 0 as the left-hand side, and you get, actually, first one proves that lambda I is n minus 1. Okay, that's the important part. When you multiply by xi here, this becomes 1 minus xi xj, which is exactly what this guy is. So this really adds to n minus 1. And therefore, lambda I is the same constant. Okay? Then when you sum these up, you end up with the centroid being of that system lying at the origin. And we also get that summation of these values, Rij over j, will be exactly n. Now, we start with some auxiliary results, and I'll speed up a little presentation, maybe not go into much detail, because I want to leave time for questions. This is the reduction rank, rank lemma. So let us denote B and A, these matrices. Bij, the matrix B, is the reciprocal of these square of distances divided by 2, 1 minus xi xj. That's what Rij is. And then Bii is really, n minus 1 minus the sum of the rest. So every row, when you add them, you get n minus 1 as a result. Okay, so the diagonal element is determined from the other ones. And Aij is just a constant minus the Bij, and that constant is n minus 1 over n. Okay? Then if x is a stationary logarithmic configuration on SD minus 1, which really means it satisfies these vector equations here, okay, the equation 1, that's what it is. Then the rank of A is less or equal to big N minus D minus 1. Okay, and the sum of the Aij, j from 1 to n, is 0. So let me emphasize what happens when n is d plus 2. What happens is that the rank of that matrix is 1. and this is a key. That lemma is true for higher, for larger cardinality of the set of points, for more points than d plus 2, but the difficulty, there is certain difficulty when one considers, tries to get, say, this result for 6 points on S2 or for 7 points on S3, it becomes more involved, and it works beautifully for D plus 2, but not a larger number of D. So how do we prove this? The force equations 1 and 2 can be used. Let me remind you, these are these two equations, can be used to get that the sum of Bij xj is 0, and sum of Bij, j from 1 to n, is n minus 1. Now what happens is, if you order x, the points, you form a matrix that has these, the transpose of the column vectors formed by x1 through xn, then b times x is 0, okay, and b times the 1 vector is 0. So we end up with all of these being eigenvectors, x1 through xn, and 1, actually, I would say the first coordinates of x1 to xn, the second coordinates of x1 to xn, and so on. These are the eigenvectors. And the 1 is also an eigenvector for B, but with a different number. Therefore, it's linear independent of the other points, and the other points, because X is non-degenerate, the rank of that matrix has to be D. So we end up with D plus 1 linearly independent eigenvectors. So that tells us that the kernel, the rank nullity theorem, implies that AX1 is really 0. Okay? So therefore, the rank of A is n minus d minus 1. Okay? Now, these are auxiliary results. Matrices with rank 1 are nice. Okay? And that's pretty much what our matrix A will look like. So if the diagonal elements, they're actually non-negative, and we take the square root of them, let that be AI, for the positive ones, and then for the negatives, AI to be negative of the square root, then one can write down what the elements of A will have to be. And we also have that C minus AIJ is greater or equal to 1/2, and then the sum of 1 over C minus AIJ is n. All right? And if AI is 0, then the ith row and the ith column in A are 0. Xi is equidistant to all the other points. So pretty much this is a consequence if we assume that one of these elements is 0. And what we, by ordering these guys from A1 down to AK, these being the positive ones, and then the negative being from AK plus 1 to AN. So let these, this is a supplemental theorem, let A1 through AN be real numbers that satisfy these assumptions, that sum of 1 over C minus AIJ is n, and C minus AIJ is greater than 0, where C is n minus 1 over n, then the first k are equal, and the others are also equal. Okay, that's the conclusion. And this is a technical lemma that if we have A1 through AN as supplemental in the supplemental theorem, then TI is that sum will have to be n minus 2. Now observe that this is true for all of the i's, right? And the ai's will have to be less than square root of c. Okay, c being n minus 1 over n. So the proof of the technical lemma consists of, well, that's technical, so I will not go into the detail, but I send the slides to the organizers. They can put them, and the paper is certainly on the archive. So I want to say a little bit about the proof of the supplemental theorem, okay? So in the supplemental theorem, we consider that function, ft, which is sum of c minus aj squared over c minus t aj. And then from the technical lemma, we derive that the value of ai is n minus 1. Now the second derivative can be computed to this quantity. And by the technical lemma again, we see that this function is actually convex. Now imagine this function is convex, or minus square root of c to square root of c. And it takes on the same values at all of the ai's, okay? And this is a fundamental observation that I want to credit to Oleg, that a convex function that takes on the same value, there can only be two values, all right? And that is why you end up with all of the positive being the same and all of the negative a's being the same. So this is a fundamental piece of the proof. Now, of course, that's not all right? We're talking about the degenerate, equidistant, and relative minima cases, and there's much more that goes in. By this point, we have proven that the best or the optimal configuration is the two simplexes. But there are classifications of the relative minima or the critical numbers, saddle points, that require much more, all right? And this is the proof of the degenerate case. Now, I did mention you just flip the pentagon, one of the sides, you rotate so that it becomes vertical, and the configuration is no longer degenerate, and the energy is minimized. This is performed here for general H. The equidistant case, the perturbation that I want to show you, that two segments, one going up, one going down, these are two simplexes. So we will consider the case where we have the configuration X as being one point that is equidistant to all the others. And now these all the others are actually two orthogonal simplexes, one with dimension, with cardinality K, and the other with cardinality L. So all of these will be negative 1 over n minus 1. That's because the equidistant property. And then what we can do, we can take these to be 0 as, we project them onto the equatorial hyperplane. And this last coordinate will always be negative 1 over k plus 1. This is the altitude coordinate. But this m minus 1 coming from, I think, well, I don't think that should be m, but most probably should be Yeah, so I'm using 1 to K and I'm using 1 to M. So not L, but M. I apologize for the typo. This should be a little M.
Yeah, Peter, there is
Yes,
really little time left.
yes. So what this is, that move or transformation or perturbation that decreases the energy, and the okay. So this is the relative minima case. All right. I don't think that's the equidistant. That is that these are relative minima, and the only relative minima are two orthogonal simplexes. Now let me give you just the idea. I will not go. This is the end. So if we have like S3, there are two options for orthogonal simplex. One is a segment and regular tetrahedron, and the other is two orthogonal equilateral triangles. Okay, so this separation will be either 2,4 or 3,3. Okay, so 2,4 is a local minimum. The global one is 3,3. All right, and that's true in general. The local minima are only orthogonal simplexes. And this is some really nice techniques with, Olympic type inequalities. I apologize for not having enough time to actually, show this. This is how you do the perturbation to show that indeed any perturbation to a relative minimum will actually result in higher energy. All right. So I want to thank you for your attention. Again, apologize for lack of time, but one needs to introduce a lot of things. So thank you.